This video is going to be about assessing and adjusting your dead time constants in probe for EPMA using the constant K ratio method. So dead time is simply when the detector is busy, so to speak, and unable to count an X-ray because it's currently counting run. So as count rates go up, we would expect, for instance, with increasing beam current versus counts per second, we would expect a linear relationship in the ideal scenario. But because of the detector dead time, as we get more and more counts, we end up with a situation where some of those X-rays that are being generated in the sample are not able to be counted on the detector because of this dead time problem. And as you can see, there'll be a discrepancy between what it should be, and it'll be some amount lower based on the curve, based on these dead time constants. This can also be a problem when we look at concentration. For instance, when we're measuring a standard and then an unknown, and let's say we're doing some trace elements, we measure our primary standard, which is some major element compound, and then we go to measure unknowns, and you can see here that we could have a scenario where dead time would cause a problem because this would be the constant or the counts per second we should measure at this concentration, when in reality we're getting some value somewhat smaller than that, and that's going to translate to our unknown and cause accuracy problems here as well. So what we do with dead times is there is this dead time constant that goes into an equation, and the software essentially puts back those counts based on this dead time correction equation. So we're going to talk today about how to evaluate the dead times and whether or not your dead time constants are correct, and how to change them in probe for EPMA if they need to be. The conventional method for getting a good dead time constant was essentially to measure a sample, some element on your spectrometers at a variety of increasing beam currents, and getting a plot, something like this orange line, and then fitting the dead time equation to it to back out a dead time that you would then put into your software. This has a few limitations. One, it's pretty close to linear, and it's quite difficult to get a good fit that is really precise on this. You would have to make a lot of measurements, particularly at these higher beam currents, to get a good, consistent dead time. And there's other potential artifacts that could cause troubles with this methodology. So instead, we're going to use probe for EPMA's constant K ratio method. And before I start with an actual example of going through the process, I would like to point out that here in the help menu in probe for EPMA, there is a helpful document that gives you pretty much everything you need to know, and almost everything I'm going to talk about in this video and much more. So you can always refer back to that for guidance on how to perform this down the road. So fundamentally, what we're going to do is, instead of measuring a single standard at a variety of beam currents, we're actually going to measure two standards with significantly different concentrations of the same element in them. And we're going to look at the K ratio, which is simply the intensity of the unknown over the intensity of the standard. So we're going to pick a couple of standards with different concentrations. We're going to select the one with the most concentration as our primary standard, and then we're going to evaluate the K ratio of the secondary standard based on that primary standard. And as you can imagine, if your dead time constants are good, we should be able to measure that at greater and greater and greater intensities, and that K ratio should remain relatively constant. This means we have to maybe make a few less measurements, and in my experience, it seems to be much more precise in terms of getting the dead time ratio correct. It also, we won't go into it in this video much, but it also can show you interesting artifacts, other artifacts in your instrument, such as the calibration of your pico ammeter, tilt in your stage, and probably other things that I haven't even thought of. It's quite sensitive and quite a powerful technique for evaluating the condition of your instrument and how well it's tuned. So the first part of the process is choosing appropriate standards for this measurement. So first thing you need to make sure is that this is going to be a robust standard that can take a fair amount of beam current without TDI or sample surface damage or carbon coat damage, because we don't want those other effects to be obscuring the dead time correction that we're going to make. So it needs to be tough, and it needs to have two standards with a approximately factor of 2 to 4 difference in concentration. Also make sure it's something that's going to give you the count rates that you need. In terms of my instrument, I have PET crystals on all 5 channels, so with just one pair of standards I could measure my dead times. In this run I was experimenting with the hafnium L line with my H-type spectrometer as well, but probably unnecessary. You should get the same results, and in fact I've confirmed it. It doesn't matter whether I used hafnium L alpha or I used the titanium K alpha. I got the same results. So just be aware, if you have, say, an L type spectrometer or an H type spectrometer, you may have to run separate routines to get all of the data, just because of the different count rates and the different types of spectrometers. So once you've chosen a set of standards that's appropriate for your spectrometer configuration and the count rates and currents you're going to be using, we need to make a new sample setup and get the instrument completely tuned up and ready to go before we make our measurements. I've already made a new sample setup. Here you can see I've got titanium on 4 of the spectrometers, hafnium on my H-type. Because of the much higher count rates, I used the hafnium L alpha, so I could go to higher currents with the other spectrometers. And I used MAN backgrounds just to save a little time. And that's not a problem. You can use conventional backgrounds, but MAN will just save you that background collection time. So then we're going to want to peak and tune the spectrometers. So we're going to acquire a PHA scan and peaking scans for all of these elements. An important note about the PHA, you want to collect the PHA scan at the highest current that you're going to be using in this experiment. In my case, I'll go here to show you the PHA scans. On a Joule instrument, I think it's a little different on CAMECA, but the principle is the same. As you increase count rates, your PHA peak is going to shift towards higher bias voltage on the Joule instrument. And so what we want to do is we want to get that PHA setting set for the absolute highest count rates we're going to see here. And we also want to make sure in our PHA settings that we have it set on integral mode. So do not check the differential PHA mode, because as our PHA slides with higher intensities, we may move it out of the window if we're using the differential mode, and we'll lose counts basically, which will skew your dead time results pretty significantly. So you want to use integral mode, and you want to calculate your PHA peak at the absolute highest current that you're going to run in the overall experiment. So now we're going to make a series of sample setups with increasing current, so we can measure our K ratio and see how they change with intensity and adjust our dead times because of it. So it's probably a good idea to do a little reconnaissance work ahead of time. Use the chart recorder or whatever you have, a sort of instant counts per second meter. I'm sure CAMECA has them. The Joule has a chart recorder. And just do a little bit of recon after you've peaked and set all your PHAs. Do a little bit of recon and see what count rates you're getting. And then you can decide what currents you're going to use in order to set up your dead time correction. I've already done that here, but I'll show you really quick a little trick I use to make the sample setup a little bit faster. So we need to change the current for every setup, and then we're going to run it after the fact using multiple setups. So I just come into acquire and make a new sample setup, call it, whatever the nanoamps I'm going to use. So we go 5, and then rather than change the conditions now, if you change the conditions here, it's going to set them on the machine, and you're going to have to wait while it sets it, et cetera, et cetera. So I actually just come in and make all of the sample setups immediately right now, 20, whatever I'm going to do through my setups. And then I'll come in here in analyze instead of acquire and change those conditions. So I can come in here, go to conditions. I want that to be 5 and then hit OK. I can do 10 and set that to 10. And now I don't have to worry about the instrument constantly changing conditions while I'm doing this and waiting 10 seconds while it finds the current, et cetera, et cetera. I can just change them all here in analyze. Once you've got all of your conditions set, so here's what I did previously with this. You want a good spread. Definitely want to get some in the low end. It's more important to get up here into the higher count rates above 5, 10,000, because that's where the dead time really comes into play. You may also want to alter the the count times individually. So you can see here in this one, I've got my count times are quite high, right? Because at low current, I'm getting fewer counts. I'm not going to get as good at counting statistics, and there might be a little more slop in my measurements. Versus up here, I'm going to be having 100,000 counts. I don't need to count near as long, so I've shortened the count times dramatically there. So that's not a bad idea. Depending on how much time you have, there's no need to count for a minute at 300 nanoamps versus 10 seconds at 5 nanoamps. You're going to have some pretty poor statistics. So it's not a bad idea to also adjust your count times based on the current and the count rates you're expecting to see. The last bit of housekeeping we're going to need to worry about is we want to make sure that our standards run as pairs and that our primary standard runs before our secondary standard, however we have that set up. So in my case, I'm going to be doing rutile and strontium titanium oxide, and in this case, they're in the correct order for me. I have the higher concentration one first and the lower concentration one second. I don't see that there's any reason that you couldn't run the lower concentration standard as the primary standard if that's the order they're in. You just want to make sure that you don't assign the standard value in standard assignments. Since my rutile comes first, I want it to be the primary standard. If my strontium titanium oxide came first, I would want it to be the primary standard. And that's because we don't want a situation, the way PFE calculates the K ratio, it assumes the standards first and then the unknown. And so since we're running that standard over and over again, we're going to have each unknown bracketed by a standard. And if the primary standard is second, then let's say our 10 nanoamp standard is going to be correcting or creating the K ratio for the next one in line, which might be the 20 nanoamp secondary standard. So we just need to make sure that the primary standard, however you have them in your list, the primary standard needs to be the first one that's run out of your pair, so that the two of the same current are going to be calculated together. And the last bit of housekeeping we want to do before we start is we want to go over here to the main PFE window, analytical, analysis options, and we want to make sure this use automatic drift correction on standard intensities is not checked. We want that unchecked. In a normal situation, when you're running unknowns, you run standards. If you run the standards twice at any point, PFE will automatically drift correct between the first time you run standard A and the second time you run standard A, and it will interpolate between those two values and apply that intensity to the K ratio for the unknowns in between. In this case, we want each pair of primary and secondary standards to stand on their own, right? So we're going to run primary standard at 10 nanoamps, secondary standard at 10 nanoamps, and then primary standard at 20, secondary at 20. And so we would have a situation where our secondary standard is bracketed by two standards run at different currents. And we don't want to introduce any extra error into that, particularly if there is a dead time problem. So we want to make sure that this value is unchecked. And it is, so we're good to go. So now that all of our setups with the different conditions are ready to go, and we've peaked and done our PHAs and gotten the instrument all tuned up and ready, we're going to apply these setups to our standards, and we're going to run these to get our constant K ratio measurements for our dead times. So here I've got all the sample setups that I'm going to run with the different currents, and I've selected them all in Analyze, and then I'm going to hit Add to Sample Setups. And that's going to transfer those into the sort of sample setup bin that we can choose from over here in Automate. So then I'm going to go over and Automate. I'm going to find myself some good positions on the samples. I'm going to add in Digitize. I'm going to drive to where I want to go and go to Rutile. I'm going to put some points in ready for analysis. And then I'm going to come over here, I'm going to select my rutile, and I'm going to select my strontium titanium oxide, and I'm going to hit this multiple setups button. And now we have all of our sample setups here. Now, some key important things to do here is we want to make sure to run our sample setups one at a time. So there's two options here. You can add all these sample setups to your standard, and PFE can either go to that standard and run each setup until it's done and move to the next standard and run each setup again. Or what we want it to do is we want it to run setup 1 and then go to the other standard and run setup 1 and then go back to the standard and run setup 2 and for both standards, etc., etc. So we want to run each setup one at a time. So it's going to run the first setup on both standards, then the second setup on both standards, etc., etc. So we check this run multiple sample setups one at a time. You can also do, if you're concerned about beam damage and your standards are big enough and wide open enough and clean enough and flat enough, you can have PFE do an increment on each pass of the setup. So it'll run this setup, and then when it returns, it'll go and do a Y increment. And this Y increment is this value over here in the automate window. So you can change that value to whatever beam size you got, and it'll just march in the Y direction off of that, so you're not measuring the same place over and over and over again. I do recommend doing this if your standards will allow, so you don't have to worry about beam damage, especially as you get into the higher currents. You're going to be running over and over and over at very high currents in the same spot. It may damage the carbon coating. So I generally do this Y increment and run multiple setups one at a time is a must. And then when we hit OK, it's just going to say, do you want me to apply these now or for the next one? We're going to say yes, apply it. And now both of these have all of those samples set up. So now we've collected our data at the differing beam conditions using our multiple setups, and we have all of our intensities here in Analyze. And we want to go through and take a look and see how our dead time corrections are faring at the different count rates. So we're going to come over here to the main window, and we're going to go to output standard and unknown XY plots. Then of course we're going to pick standards, and there's our list of all the standards we've run in this. And we want to look at our secondary standard here. So in this case, for our PET crystals for titanium, that's going to be our strontium titanium oxide. So one thing I can do here is just type in a short string of unique text and it will select those. We're going to choose average only and scatter. I think the default is line. You're going to want to switch that to scatter so you don't have the lines in there. Average only, but you could show all of the values. I did average only because I actually did pick multiple points per run, and I recommend doing so that you get good counting statistics. Just set this up and run it overnight, come in the next morning and your data's all there, and that way you're not going to have any spurious counting statistics issues that might obfuscate the actual dead time issue you're trying to investigate. So make sure to collect plenty of data with plenty of good count times so you get good statistics. So now in our plot, we're going to do on beam current. That's the Faraday cup measurement before the analysis. And we're going to go down here to raw K ratios. Now I'm going to show them all at once here for all 4 spectrometers I did titanium on. I would recommend probably doing them one at a time when you're doing this yourself, just so you don't get confused and kind of keep everything in line. So, but this way you can kind of see what all 4 spectrometers are doing right now. And then I'll go through and show you how to change it if there is a problem. So average only, raw K ratios. Now let's hit output. And PFE is going to chunk through this and give us a plot of those K ratios. And there you go. So ideally, right, as current change, so this is current, we should have this nice flat line like we do here for spectrometers 2 and 4, which I've already adjusted their dead times. So we've got very little variation up to 400 nanoamps. So I don't remember what the count rates were, but I believe this is up around a couple 100,000 counts per second. So this is remarkably good flat, right? We're talking what, maybe 2 in 450. So pretty small amounts versus spectrometer 1 and spectrometer 5. These clearly are varying with count rate pretty systematically. And again, this is a dead time issue. I intentionally put an incorrect dead time in here. And in the case of spectrometer 5, you can see that as count rates go up, we're getting more counts than we should. So this means our dead time is too low. We are overcompensating for the dead time, and we have a dead time value that is too small. And here on spectrometer 1, it's dropping with increasing current, which means our dead time is not sufficient. So we are losing counts as we go up because our dead time value is too high. So real nice. And not so good, not so good. So this is something like 2% variation here. A full, maybe even a little bit more, 2 or 3% variation. So that is going to affect your analyses, obviously, if you don't have this right. So we've determined that the dead time on 5 is a little low, the dead time on 1 is a little high. So how do we change that? So let's close this out and close this out. And now we're going to go over here to analytical, and we're going to come down to update dead time constants. And this is a cool little feature where you can fix this in pretty much real time and see the results. So this is all the samples we have in here. So we're going to go ahead and select all so that we apply these changes to everything. Another cool little feature, when you select all the samples, it gives you the current dead time that these were run with. Then we want to select our scaler, which is our spectrometer. So we've got 1.1 in here for spectrometer 5 on PET-J. You can change what crystal it will only assign to. So make sure you're on the right value here because you don't want to accidentally send the value for 1 to channel 5 or vice versa. So let's put in our spectrometer and crystal, and then we're going to change our dead time. So we know it's too low, so let's raise it up to 1.3. And then I'm going to hit update dead time for selected samples. So again, make sure you've got everything selected in here, otherwise it'll only apply it to the one you have selected, and we want to see it for everything. And while we're at it, we know that spectrometer 1's dead time at 1.7 is a little too high, so let's lower this one down to 1.5 and make sure we got the right spectrometer and crystal, and we're going to hit update dead times. And now we're going to come in here, we're going to hit close, we're going to go back to output. We want standards, we want strontium titanium oxide, we want on beam current, and we want raw K ratios, and average only, and scatter plot output. And now it will show us the new values for our K ratios with that improved dead time constant. And there we have it. Now it looks like we've gotten a little closer with our spectrometer 1, but we're still off with spectrometer 5. So we need to adjust these some more. And that's all you're going to do. You're just going to iterate these until you get as flat of a line as you can. And you may see some little artifacts in here, but the real goal is to minimize the spread in K ratios that is a function of this incorrect dead time. So we're pretty close here. We've greatly reduced the problem on 5 or on spectrometer 1, and we need to do a little more on spectrometer 5. So let's go back in. We'll close this, and we're going to go to analytical, update dead time constants. And spectrometer 1 we know was a little too high. I think I remember the number that is correct, so I'm going to put that in there. I'm going to select all. I'm going to update dead time constant for those. And I think just coincidentally that value is the same for the other spectrometer, so we're going to put that in as well and update. And then we're going to close this. And then we're going to go back into output. Average only, standards, strontium, on beam, and raw K ratios. And let's see if that got it back where it should be nice and flat. And it looks kind of nasty, but that's because it's auto scaled. So we now are going, what is this, 4 or even 3 in the third decimal. So well under a % variation from essentially 5 nanoamps all the way up to 400 nanoamps. So we've got a couple of orders of magnitude of count rate changes across this and very little variation. So that's pretty good. Our dead times are in pretty good shape. So let's close this out. So the last thing I'm going to show you is how to update those dead time values in the scalars.dat file, which is a preference parameter file that PFE uses. And we're going to update those with our new dead times that we've just calculated so that every new database you create from here on out with a new method is going to have the correct updated current dead times. So we'll go to this PC, our local C disk. We're going to go to program data. FYI, this is usually a hidden folder, so if your installer didn't already unhide it, you'll have to go into Windows and set the settings to show hidden folders. We go to program data, probe software, probe for EPMA, and then we're going to find our scalars.dat file, which is right here. And then we want to open it with a text editor. Notepad will work. Notepad++ is a good free bit of software that works pretty good for this. And here we have our dead time values. So now just change these values to the values that you determined when we just did the process we just did. And you're going to then save this file, and those will be there for all future databases that you update from now on. And I think we saw in the beginning of this, if you update them here and then open an older database or import from an older database, PFE will recognize that the database and the scalars.dat file don't have the same dead times, and will give you the option to either update those with the current scalars.dat file or to keep them the same as they were for the old data. So if you're just reprocessing old data, you probably want to keep the dead times the same, although if they were wrong in the old file, then it's not a bad idea to update them and reprocess the data. But if they've changed because of something you've changed on your instrument, in that case, you might want to leave them the same as they were in the old file. It just depends on your situation. So that is an overview of how to do the constant K ratio dead time method. Thanks for watching.